My name is Mitch Belkin. I am a radiology resident at University of Maryland School of Medicine. And I'm here with my brother and co-host Daniel, who is also a radiology resident at the Johns Hopkins. We're here with Dr. Eliot Siegel. Dr. Siegel is a professor of radiology at University of Maryland School of Medicine. He led the Baltimore VA to become the world's first filmless healthcare enterprise in 1993. He's a prolific author, speaker, has written over 300 articles on medical imaging and PACS, has edited several books and given over 1,000 presentations worldwide. In addition to his interest in digital imaging and PACS, he's interested in telemedicine, the electronic medical record, informatics, artificial intelligence, machine learning, and much, much more. Eliot, welcome to the External Medicine Podcast.
Thanks. It's an absolute pleasure and privilege to have the opportunity to talk with you guys this afternoon.
Before we get started, do you have any financial disclosures?
So, yeah, I've got many financial disclosures. Let me just give you a few highlights, and I will try to make sure that none of the things that I say are really biased. But just in case, you mentioned that I'm a professor at the University of Maryland. I also have responsibility as a radiology attending at the VA Maryland healthcare system. I'm also a co-founder of a company that aspires to have a national presence throughout the U.S. In Theranostics, which is the use of radiopharmaceuticals and diagnostic imaging to treat a subset of oncology patients. I also am a founder of a company called ACREW, ACREW, that is a company that does fusion between CT and MR images and real-time fluoroscopy. And then on the advisory board of a large number of AI companies, and then have many different society roles, including being one of the deputy editors of Radiology's artificial intelligence journal, and affiliations with a number of other publications, have a number of grants that I have worked on or co-worked on that are NIH grants and NSF grants. And those are most of the highlights. I think if we wanted to go into each potential conflict of interest, we'd probably spend the rest of the hour and a half, but maybe suffice it to say that I have a number of startups and have a lot of advisory roles and also board of director roles. One thing I should mention is I'm on the board of directors of a company called Mach 7, and was just recently, but no longer, I'm on the board of directors of Carestream Health. So I think those are probably the highlights. And if anything else occurs to me that would potentially be a conflict of interest as we're speaking, I'll mention that too.
So you've obviously done a lot of things, a lot more than I think the average radiologist. Before we dive into, I want to dive into some of the specifics of how PACS got developed, and some of your other interests in theragnostics, for example, is very interesting. But maybe just if you could give us an overview of your intellectual interests and history, and how you got interested in so many different exciting ventures in between radiology and entrepreneurship.
Yeah, well, so I should also mention that a adjunct professor of biomedical engineering at College Park at University of Maryland, and also a adjunct professor of computer science at the University of Maryland, Baltimore County campus also. And so I've always been interested in technology as a kid. In fact, reading Robert Heinlein's novel, The Moon is a Harsh Mistress, when I was essentially preteen, sort of got me really interested in the idea of having an emerging intelligence. If you put it, the idea of this book that was written in the early 60s was, if you put enough computer resources together, there could be an emerging intelligence that comes from that. And so ever since I was a kid, the idea of having non-human intelligence and being able to create something that would be sort of the next evolution in intelligence was something that intrigued me. And so that brought me to have a strong interest in high school in computer science. And I decided I wanted to go into medicine during my college career, but my area of particular focus during college was the human visual system. So I actually started doing graduate research pretty much after my freshman year in the human visual system, which of course led to my interest in diagnostic radiology and kind of a subspecialty in optical illusions and some of the ways that those work. And then I had a minor in computer science. And then I finished college in a little over 2.5 years, maybe almost 3 years. And actually, while I was waiting to get into medical school, where I was accepted early decision, worked at NIH in the DCRT, which was the computer division that did research, actually, as it turned out, in AI for ECG interpretation and radiology image processing. And so I had the opportunity then in medical school to work my way through medical school, making some money doing computer programming. Actually worked with a guy named James Lynch, where we did studies looking at hypertension and the impact of various activities related to hypertension. It was actually on 60 Minutes on a program that looked at how having a dog or a pet and petting the pet, essentially, or having the pet with you, significantly decreased blood pressure. And the idea of talking, as we're doing now, actually increases blood pressure. So, I sort of had a technology background and interest, during all of my school years, working my way through medical school, and then decided after a rotation in radiology, where it just seemed so computer heavy and so technology heavy, that diagnostic imaging was the area of my interest, particularly because my undergrad work had been in the human visual system and processing visual information. And so it just seemed like it was so much fun. Plus, back then, before digital imaging and PACS, in a film-based environment, radiology was the epicenter of the hospital. Everybody had to come to radiology because you couldn't look at your quote unquote films unless you came. And so all my friends from, medical students would come by, and other people, and it just seemed like such a sociable, communicative specialty. Ironically, I ended up doing a lot to change that, in ways that are positive and negative. But I really like the idea that radiologists were kind of the doctor's doctor, and the idea of being Sherlock Holmes with the images and then having that dialogue with the referring clinician. So, as I got to my third year of medical school and was thinking about what to do, radiology seemed the perfect match for me. And my background in computer science was something that the radiology department was aware of. And so they started recruiting me. And I actually flew to Boston with the chairman of the radiology department for one of the early conferences on radiology information systems and computer automation. And so it just seemed like a natural fit. And so I decided I was going to do my residency at the University of Maryland, because I met my wife, who was a year ahead of me. There was a big brother, big sister program at the University of Maryland. And as an incoming freshman, she was a wily sophomore and assigned by the Office of Student Affairs to be my big sister. And so, we met there. She was a year ahead, so she hung around Baltimore because we got married during medical school, and University of Maryland was a natural place for me to stay. So I ended up going there for my residency.
So you decided and ended up going to University of Maryland because your wife was in Baltimore.
I think if I just said yes to that question, I would belie the fantastic program that we have at the University of Maryland and all the wonderful opportunities that are associated with the trauma center and the cancer center and all the other great things. But in a word, yes.
You were talking a little bit about radiology prior to the creation of Filmless imaging libraries and sort of the dissemination of radiologists, rather than being the focal point in the hospital, to being now people that can read from their homes or on a beach somewhere,
right,
maybe somewhere in Rehoboth.
Yeah.
Before we get into what it was that you did in the early 90s at the Baltimore VA, can you tell us a little bit more about what radiology was like before 1993 Baltimore VA?
Yeah, so radiology was a really interesting specialty. At that point, radiology was a lot less interesting and exciting than it became later. And so when I applied to radiology, radiology was of kind of average interest. And, that it was some of the above average students, but not necessarily the best and brightest students coming into radiology. Radiology at that point was not really known as being super high tech. Mainly when I essentially started in 1982, it was mainly CT was relatively new. They had stopped doing pneumoencephalograms, which were sort of a way of torturing patients in the OR by turning them in every possible direction on a table. And so at that point, radiology was really mainly plain films and barium studies. I remember talking with a resident recently and asking, how many fluoro studies that we had that morning just recently, and saying, oh, it's a really busy morning. We had 3 studies this morning. And when I was a resident, we would have maybe 20, 22 studies or so, because barium was the way that we ended up, diagnosing lots of abdominal different diseases and processes. And, when I said, 22 cases, people were laughing and telling me about when they were residents, and it was, 30 or 40 fluoroscopy cases. So, radiology was not so high tech, not so really interested in it and exciting. But to me, the advent of CT and MRI was just sort of starting to come on its own, and the idea of the processing of the CT and MR and some of the techniques and physics associated with it started to become higher and higher tech. But the people who would go into radiology was almost all males. In general, the people were not particularly technical per se. And back then, radiology and radiation oncology had just essentially split. It used to be, before I started, that radiation oncology and radiology was essentially one training program. And so diagnostic radiology had relatively recently split off from a combined program of rad-onc plus radiology. And radiology at that point also was interventional radiology. And so when I trained, the expectation was that when we finished our training, we would do all the interventional radiology studies, which were mainly vascular back then, whereas now vascular is taken over to a large extent by vascular surgeons, and we're doing more oncology types of studies. But when I was a resident, the expectation was that we would have the ability on our own, without being directly supervised, to do image interpretation and to be able to do interventional procedures. And so a lot of times the attendings would kind of turn us loose in the OR and the angio suite, come back at the end of the day and say, let's go over the interventional cases and the diagnostic cases that you did. And so residents then were much less directly supervised than they are now. There were far few opportunities to be able to learn online because there was no internet, essentially. And so what you learned was from a film-based teaching file, and what you learned was essentially from the direct training that you had, and then textbooks that were available. And journals were, of course, all only in print, and were not easily and readily accessible. And so radiology at that point had been relatively static for decades and was just about to take off. MR was emerging. PET had not really yet been introduced in any significant way, but there was more nuclear medicine that was being done, and MR was a brand new, exciting specialty that people weren't really sure exactly what the role of that would be. But at that point, things started to become more technical, and there started to become more interest by people who were technically interested in going into radiology. Women in radiology was quite a rarity back then, and still they're in the minority, but it was very much male dominated at that point. And so radiology was a specialty that was really changing extraordinarily rapidly at that point, with the introduction of MR and some advances in nuclear medicine and some advances in CT. But there was really almost no work done with digital technologies, and radiology was all completely paper-based. And so there was no radiology information system, there was no hospital information system, and everything was on film at that point.
So let's talk about, you've set the scene nicely. Let's talk about PACS, which I have to look up every time, but I wrote it down, and it stands for Picture Archiving and Communication System. What is PACS for people who aren't in radiology? And then maybe give us a sketch of what the different threads were that led you to implement that at the VA in the 1990s.
Yeah, so it was kind of being at the right place and the right time. There were certain things that had to exist in order to allow one to go digital. So I guess the first question was, would it make sense to have a digital department instead of an X-ray department? And so the answer to me was obviously absolutely yes. I mean, having my experience playing video games, there was a great video game system called Plato, which was University of Illinois, that was used for educational purposes, but that was available to medical students for education. And that was kind of the closest thing that I had to the internet, where you could essentially communicate with other people, send the equivalent of emails, and essentially have online learning information. But the internet in general really, was not there at that particular time. But I became convinced that the idea of information at your fingertips would be a really important thing moving forward. One of the challenges that we used to have was that the films would disappear through the hospital. And you had this chicken and egg problem of everybody would take the films to make sure that the films would be available to them when they needed them. The vascular surgeons, general surgeons, orthopedic surgeons in particular. But because they took the films weren't available when other people needed them. So it became a self-fulfilling prophecy. And of course, the film could only be in one place at one time. And so the idea of access to films was huge. We would have fights with the surgeons constantly. And one of my attendings, who was a, famous attending for being extraordinarily forceful and emotional and I guess strong, but very aggressive and very mercurial and direct, Dr. John Diaconis, for a time was the head of the department, and he had stepped down to being one of the attendings at the time. And he was famous for fighting with the clinicians about getting the films back. So he would round upstairs in the hospital, find all these films lying around, yell at the people who had taken them, bring them back to radiology. And of course, they would disappear then again from the radiology film room, and there would be this constant struggle. And of course, the medical legal liability associated with films not being where you wanted them to be was huge, because if there were ever a medical legal case, you had to produce the films, but of course they weren't there. One of the comments that was made by the chief of medicine when we went filmless at the Baltimore VA Medical Center was the chief of medicine made the comment that Baltimore VA had always been filmless because you could never find the films when you wanted to find them. And that was really a true statement. And that became kind of a rallying cry for us. So one of the reasons that we wanted to, go digital was because my experience with an early version of the internet that was just available to academic sites and in particular medical schools was that I was spoiled by having access to information essentially on that pre-version of the internet. And the idea that we could set up our own image management system or picture archival and communication system was really intriguing. And then, of course, at that point, I was very much into the mathematics and science of image optimization. And so being able to do edge enhancement and being able to change the lookup table so that you could present more information on the darkest dark and the whitest white in the images to be able to minimize the need to be able to change, let's call it brightness and contrast and what we'd call window and level. The ability to be able to mathematically compress images, process images, optimize images And then, of course, the idea that a computer would be able to make a diagnosis. So even back in the 1980s and early 90s, people had created some software that would do computer vision. And the idea that one would be able to, at some point, use the computer to be able to find pathology faster than radiologists, or to be sort of the equivalent of a spell checker, for example, was really intriguing. And so at that point, I was in a really interesting position where I was finishing my radiology residency, and I was asked by the chairman at University of Maryland to stay on. And he had asked me if I would consider taking over the chairmanship at the VA. So here I am, a fourth-year medical student, and being asked to stay at the VA, which normally would not have even been an option for me. But the offer was, would I be interested in staying on at the faculty at University of Maryland, being able to be in charge at the VA, which would make me in charge of so many of my attendings, who rotated between the University of Maryland and VA, which were in separate locations in Baltimore at the time, but that changed later. And then also the idea was we were going to build a new hospital that was going to open in 1993, maybe about 6 years or so, 7 years from when I was finishing up my residency program. And the idea to be able to, from an architectural perspective, plan the department, be able to purchase radiology equipment, state-of-the-art equipment in this new hospital. And I asked the question and kind of made it contingent, would it be okay if I also tried to create a completely digital department? And so I didn't have a huge amount to lose at that point because I'm just coming out of residency. And so at that point, nobody had ever done that before, and people did not believe that it was possible to do that. And in fact, the pundits that I talked with around the country thought that it was too early to do that. And so I had to figure out, under the assumption that it would be possible to do that, what were the missing components to be able to go digital? And it seems like a pretty straightforward challenge, as you guys might think of it now. Sure, if you've got a computer, you've got a workstation, you've got images, but there were multiple really fascinating challenges that were huge headwinds and that were hurdles to be able to do it, such that nobody had ever done it before. And so I had to identify what those hurdles were, which now may be amusing or anachronistic, and then figure out how to jump through those hurdles, and in a federal system and in a new hospital, be able to open that as completely digital. And to me right now, thinking about the odds of being able to pull that off, they seem incredibly steep. But back then it just seemed like, I'm out of residency. It seemed like a really cool, fun challenge to do. And so it seemed like a great game to play. And I really thought that I could pull it off at that point. And so the adventure was identifying the hurdles, figuring out why nobody had ever done it, and figuring out what were the pieces that would need to be put together to actually pull it off.
So tell us a little bit about these specific hurdles that you faced at that time. I'm also very curious. You referred to them as pundits. What was it that people were particularly concerned wouldn't be functional about going all digital in the early 90s?
Yeah, so let's talk about some of the hurdles. One of the hurdles was the cost. And so one computer workstation from Siemens that was designed to read CT and MR studies associated with just their own modality was an 8-bank workstation. And the reason it was 8 banks was because radiologists on film had displays that were that had essentially 8 large frames to put 8 films up. And so the alternators in the view box back then had the ability to put up many images. And the reason is because if we were generating 40 or 60 images with a CT or MR study, it would take a lot of films, and you didn't want to be putting films up and down again. So the original assumption was that in order to interpret cross-sectional studies with lots of images, you'd need lots of monitors. One of those monitors cost about $280,000. back then, and 280,000 back then was, would be even more now, given the adjusting for inflation rates and cost of living, et cetera. And so it was prohibitively expensive. So the first hurdle was, can anybody put together a system that would allow us to be able to have less expensive workstations? And so that was one of the things. Would there be a vendor? Would there be a platform that would allow us to do that? And so it turned out that that was one hurdle. The second hurdle was these images were fairly large. I mean, a chest PA and lateral study, may have been a few megabytes or so in size. A CT and MR at that time also was a few megabytes. And so as you ended up putting these imaging studies together, you would find that in a day, you might generate somewhere in the neighborhood of 5 gigabytes, 10 gigabytes, something like that of data, even back then in a department. And so the problem was, how do you store those data? So at that point, there was no media to store data of that size. So we ended up having to get an optical jukebox that was made by Kodak, that the day we bought it looked like it should be in a museum in the Smithsonian. It was this monster device with 15-inch platters, and it had dozens of these platters, and it would be this mechanical arm that would run and get the platter and essentially load it up so you could get it. So all the platters together for the whole hospital, the whole department, and everything, the cost of the storage for that was $800,000. And so how much storage was available for the whole hospital associated with the entire PACS? 1 terabyte. So I can buy a terabyte at Best Buy for about $40 now. And so the problem was, there weren't a lot of aliquots of $800,000 back then. And so we had to figure out how to make 1 terabyte of data store all what we needed for, let's say, 5 years, even though theoretically, the storage would have been eaten up within a fraction of a year, essentially. So then we had to figure out about image compression, and was image compression safe or not? And then at what levels, and what was the degradation? So I did a lot of research in image compression and learned a lot about wavelet compression and cosine transforms and all the math and science associated with that, which was part of what we needed. The other thing was the resolution on film, on an X-ray film, might be somewhere in the neighborhood of about 10, 20 line pairs per millimeter. So really super fine resolution, because this was the grain of film. But on the workstations at the time, the displays were more like 2 megapixel displays were the highest, and those monitors were, $10,000, $15,000, $20,000 or so a piece. And they were CRT monitors, so they were incredibly heavy, and they put out a huge amount of heat. And what we found was that their life expectancy was relatively low, because they put out so much heat, the rooms got really hot. So one of the objections was, we can't switch to monitors for cervical spine radiographs and mammograms and other studies, because you're losing out so much in resolution. So we had to do research to show that contrast resolution, windowing and leveling, brightness and contrast, was more important than resolution. So we had to essentially get past the hurdle of, the monitor's not quite as high resolution, but it doesn't matter. It's okay to compress images, and still when we compress images, we're medical legally okay. The lawyers told us that the law was we had to store images on film for 6 years. And so that made sense. I mean, retain images for 6 years. But the lawyers told us that the law said they had to be stored on film. So inherently, if we never made film, then we would be violating the law, because we wouldn't be storing images for 6 years on film. Of course, that's convoluted logic. And the answer is, well, we're going to store them digitally. We can print a film whenever we want. And so getting the lawyers past that idea was a huge issue. The next issue was, when you go to the CT scanner and you have a patient that you want to scan, Eliot Siegel can be spelled 100 different ways. You want to have 2 T's in Eliot, one one L and Eliot, two L, Siegel, is it Seagull, or is there another spelling of Siegel? And then there are errors in typing that in. And so it became clear you needed to have a hospital, at least a radiology information system, so that people could order studies. And all the ordering, of course, was on paper. And back then, the culture was doctors don't type. Secretaries type, maybe ancillary people type, but doctors didn't know how to type back then. Nobody could close their eyes or look at the screen and type unless you were one of the anomalous people that essentially had taken typing in high school. So, the transition of people to requesting studies electronically, was part of the issue. And then having a system that would communicate those requests directly to communicate them with CT scanners and MR scanners and modalities was an issue. Another issue was the fact that the way we captured the image for, say, a chest X-ray was using film. In other words, so you had to figure out and invent another digital technology to be able to capture the data, because otherwise, when you captured the image on film, and back then everybody was taking photographs on film, but when you captured it on film, you'd have to put it into a film digitizer, like a fax machine, essentially, for a film, and then digitize that. So then Fuji and then later Agfa came out with a photostimulable plate, essentially something that looked like film, but actually captured the image and could be read out directly digitally. And then years later, direct digital capture came out. So in order to pull off PACS, you'd have to pull off an electronic medical record system that would allow you to request studies and have those communicated to the various modalities. You'd have to solve the issue related to compression. You have to solve the issue related to monitors. And you'd have to solve the issue related to the expenses associated with things. You'd have to train people to be able to use a mouse, because radiologists back then didn't know how to use a mouse or a trackball or computers. Most of them were not computer literate at all. You'd have to get the surgeons to buy into the idea of not using film after they had spent years and years getting used to film and drawing on film with crayons and everything. You'd have to essentially figure out a mechanism to be able to store the data, as we talked about. And so there were so many unique challenges of things that people had never done before. But fortunately, what was great was that it was a new hospital, so we could build some money, about $6 million, into the line item of the new hospital. It turned out that with a new hospital, we had the excuse to be able to say we're going to do something new and different. In the VA, we were able to tell the clinicians and radiologists, this is the way it's going to be, because you're employees of the hospital. And we realized that maybe you're not enthusiastic about giving up film, but that's how things are going to operate in the hospital. We had the ability to have some dollars set aside for the digital storage. And then we had the ability to be able to work with the vendor to get promises that they would guarantee the monitor. So if a monitor burned out, which they did because the rooms got so hot, because the monitors put out so much heat, that we had to replace the monitors on a regular basis. And then we had to convince people that it was as accurate to read images from a computer workstation for chest radiographs, C-spine studies, other plain film type studies, and do that in order to be able to have them feel confident that they weren't missing out. And then we had no idea how long it would take to read a study. So when you had a chest PA and lateral, for example, you could now window and level the image, and you could zoom the image. And so one of the things that people suggested was you could play with an image all day. I mean, when the films were already loaded by the film room people, and you just walked up to an alternator, we'd have radiology attendings who'd keep their foot on the alternator, and they would just constantly move. They could read the images so fast and dictate as the images came by. But one of the questions was, would people spend 10 minutes windowing and leveling and zooming and moving around in the image? Oh, let me take a look through the abdomen at the L3 vertebral body. And no one had any idea, if you had an infinite amount that you could do on the workstation with the image, how much longer it would take to read the images. And so those were all issues. Right now, if you're looking at a CT or MR study or PET CT, for example, of course, you stack all the images on top of each other and your eye is able to integrate to see if there's a new lesion or nodule that pops into sight, and your eye has some, and brain have some motion detectors, which is along my area of research interest as an undergrad. But it took me years to convince our cross-sectional CT and MR docs to not put the images up on the monitor, and we settled on a 2-monitor workstation or 3-monitor workstation for the most part, to stack the images. It took years to convince them not to make them look like film, but to essentially stack them on top of each other. And to show them that that was more accurate and faster. And it took, so those were all huge questions that nobody had ever been in a position to be able to put together all of those different components and take the risk that it wouldn't work. Now, the Army did the same thing at about the same time, and they created an RFP, a request for proposal, in the Army, the Medical Diagnostic Imaging System, MDIS is what it was called. And they bought the system at the same time we did, in essentially the same system. It was Siemens and Lockheed. The reason we went with Siemens is that they were able to create a proprietary network using Apple computers, Apple IIFXs, and then Quadra 850s. They put that network together, and so the workstations cost about $10,000 a piece, but at least not $280,000 a piece. And then we had reasonably high resolution monitors associated with those that were CRT monitors. And so we were able to get the computer workstations enough to put them in strategic places like the ICUs and the ER and the ORs and some of the team rooms, but certainly not absolutely everywhere. And then we were able to, after that, figure out the network itself was put together, and the storage. It turned out that Lockheed Martin essentially, had been doing work with secret military spy satellites. And the spy satellites were doing top secret work that was supported by Lockheed, where they would record, and they would record as much of as a terabyte of data that they'd have to store, and they had networks where they had to move the data around. So Siemens partnered with Lockheed, who provided a proprietary network. The hospital didn't have a network when we installed PACS. There was no such thing as Ethernet. There was no hospital network. So we had to lay our own fiber. Instead of using essentially Ethernet cable, we had to lay fiber and use a special network that was not a standard network. And so we ended up doing those things. Doing that in a not new hospital would have been really a daunting task. But since it was a hospital that we were constructing, they were able to prospectively lay the cable, the optical cable, everywhere to connect the workstations. And so all of those things ended up coming together. And my full-time job as the head of the department for the first few years after I took over in 1986, 1987, was really planning the PACS and doing the things. And of course, running the department was kind of a side job, and ended up doing that also. And of course, we had to pick all new radiology equipment. But, those were some of the obstacles related to making the transition. One of the things that we found was that it was hard to get the clinicians who were, saying internally to us initially, I heard, listen, Sonny, you're 20, you look like you're 20 years old. I've been an orthopedic surgeon for 50 years. You're not going to tell me to give up film. So we had CNN come in with actually the senator at the time, Senator Barbara Mikulski. And CNN did a big interview, and I asked them to interview the surgeons and the head of medicine. And they asked the surgeons and the head of medicine what they thought about the PACS system. And of course, they knew the game. They said, oh, we're excited. It's super high technology. Once they found themselves on TV and on CNN saying how wonderful it was, we could just play that back to them, and tell them, hey, we're excited that you're excited. And so, kind of like a kamikaze mission at the new hospital, when we opened, we didn't have any light boxes. There was no backup. Whereas the Army at Madigan Army Hospital and in Hammersmith in London, where they also bought the system from Siemens and Loral Lockheed. The Army bought it from Loral Lockheed with Siemens as a subcontractor. We bought it from Siemens with Loral Lockheed as the subcontractor to Siemens. But in any case, they didn't have an electronic medical record, and they installed the PACS in a hospital that already had film. And so because it had film, they took 4, 5, 6, 7 years to make the transition before they turned film off. So they offered both. People continued to use film and had PACS as a convenience, and then they slowly transitioned. We opened the new hospital in 1993, in June of 93. There was no alternative, which was scary because things were running late. Siemens, for example, told us that there were issues with DICOM and compatibility, even with their own equipment. We told them, tell it to the director of the hospital, because we can't open the new hospital unless we had the systems running. So we were able to use as leverage the whole hospital and the disaster that would happen with public relations if the hospital was not able to open because people weren't able to deliver on time for components. So I use that. One other thing that you should know that's interesting is that although the standard for medical imaging is DICOM, each medical device like CT, Siemens MR and CT and GE and Philips and the others essentially had their own different flavor of DICOM. So we had to have a system that translated all the versions of DICOM into a standard, one arbitrary version of DICOM that existed. The biggest advantage that we had at the Baltimore VA, which helped me incredibly, was the VA had the first electronic medical record system, what it called DHCP at the time, and with an overlay that's called CPRS. The VA had an electronic medical record system. So we could take orders that were put in on radiology studies, and working with IT at a national level, they were able to support us in doing the interfaces between the EMR and the radiology information system built into the EMR and the PACS. So having a new hospital, having the EMR, essentially it was existing where EMR did not exist in the vast majority of hospitals in the US at that point. Having a new hospital where we could build in our own network, and being able to have a system where you had the physicians as employees rather than as separate contractors, where they essentially, had less ability to object to a major transition to, digital operation. So it's kind of like with my secretaries, when we introduced the word processors and said they were going to switch to word processors, they didn't want to give up their IBM Selectric typewriters because there was a learning curve to learning how to use a word processor. And it took years, at least a couple years, to get them convinced. And of course, they'd never go back now. But there was a similar transition with radiologists and clinicians to get them to use a computer in an era where the majority of physicians were not able to type and were not able to, did not feel comfortable. I mean, most of the people, their first experience with a mouse was with the PACS system back then, even before they got a home computer. And that was still kind of an era where people were just starting to buy home computers. So all of this may sound incredibly daunting, but it was a fun adventure for me. And at that point, I was in my upper 20s. I'd just finished residency. And so, at that point, having the energy, having this be really kind of a fun game to play, it ended up really being energizing for me. And, as we ended up opening the system and it ended up working, we would have visitors from around the world every single day, one in the morning and one in the afternoon, who would just come to observe the idea of having filmless operation. And so, even after we implemented, that kept me busy for a while too.
This is just an incredible story to hear. One thing that is very striking about all of this is that this took place within the confines of the Veterans Affairs Administration. And I know that this was, of course, a new hospital, so that offered a number of advantages, though it seems like there was still infrastructure previously with, having the CPRS or whatever it was called prior to being called CPRS in existence. But in terms of like functioning within a highly bureaucratic system and getting something like innovative to come out of this, how were you able to operate in that sort of environment to do something really big?
Yeah, that's a really insightful question. So the VA back then, there was no information security officer because there was no electronic medical record. There was no data. IT at that point was really very creative and very willing to work and do cool things, because at that point, before the era of the electronic medical record, the people who were doing IT were kind of pioneers in the electronic medical record anyway. I mean, an analogous question to yours is, why did the EMR develop in the VA before it did throughout the rest of the academic world and throughout the rest of the private practice world? And the VA had some really creative innovators who essentially created the first electronic medical record system that was based on mumps and related to the Mass General system that had been created by some pioneers there. And so a lot of those same pioneers were still around in the late 80s. And Dr. Ruth Dayhoff was a pathologist who pioneered her own homegrown imaging system as part of the electronic medical record at the Washington VA. And she had a technical colleague, Peter Kuzmak, who helped her, and they were super supportive of the idea of having interfaces built to the VA system. At that point, the director of the VA was really supportive of the idea of having a high-tech, innovative program associated with the new hospital. I mean, the idea that Senator Mikulski could come, and one of the things to really crow about, in a system that, had had so many setbacks as far as bad press for the VA, being able to open up with a super high-tech look and feel and a digital system was really amazing, for them, because we ended up getting a lot of senators and people from Congress. A few years later, we had then President Bush, who came by to announce the meaningful use and to announce the transition to digital for the electronic medical record for all hospitals throughout the U.S. He came to Baltimore and talked about the Filmless digital radiology department. And so we would have visitors from DC. And so the hospital became known, because of the PACS, as a super high-tech, innovative hospital. And so that became part of the identity. And so it inspired the imagination of a lot of people in the VA who at the time were innovators in the IT space. If I had to do it today, I would have a lot of bureaucratic hurdles, just as you're suggesting, because of sign-offs from IT and information security and issues related to getting support for interfaces, that can take months or years sometimes to be able to get those through. None of those barriers existed. I was able to make a phone call to somebody who would recommend somebody else and do this essentially by meeting people in person. The head of radiology for the VA at that point, who was in Washington, D.C., was super supportive of a really cool, interesting idea. So your point that of all the places in the U.S., I mean, Stanford, Mass General, some of the more progressive private practices, I mean, where would you expect the world's first digital department to be? Most people would have put the VA at the end of the list, but because there were so many unique things about the VA, in particular, its electronic medical record, it really allowed me to be able to pull off the first system. And then, I had relatively little support from a people perspective. We had to kind of pull it off with our own personnel. So I would go to PACS meetings that were held by our vendor with the Hammersmith Hospital that was contemporaneous for us for buying PACS, just not implementing it, and the Army. The Army would bring 50 people, 8 physicists and 11 engineers and a whole host of IT people to every meeting. The Hammersmith Hospital would bring about 12 or 13 people. And then when they said, well, who's here from the VA? It would just be me, essentially. And so in some ways, that was a disadvantage because I didn't have that army of people. But in many ways, it was an advantage because really I was able to make all the decisions without it having to go through a committee structure. And then I just had to interface. So it became a really cool first project of mine to be able to pull off. And, the odds of it being successful may have been less than 50%, but all of the things ended up just coming into place. And so, we were able to pull it off when the hospital opened. We opened Filmless and digital. We had, Senator Mikulski, CNN, some other media come in. And then we had visitors from Europe and Russia and China and all over the US. Every hospital that subsequently went digital into PACS, every one of them made a visit to the Baltimore VA before they did. And then we created an imaging informatics fellowship a few years later that encompassed a really broad area of different topics. But having the world's first MRI scanner means that any part of the body that you scan, the big toe, the little toe, the left earlobe, anything that you image becomes a publishable article because no one's ever done it before. And the same with having the world's first PACS system. So we really became a definitive, academic source because for quite a while, nobody had another PACS system. It took a few years actually for the second all digital hospital in the US to come into play.
Well, there's a lot more to talk about on this topic, but unfortunately or fortunately, you've also done a lot of other really interesting things, which I want to at least touch on since you're with us today. So the next topic that I wanted to hit on is Theragnostics, United Theragnostics, which is one of your companies. And I know it's a very interesting company. It's doing, and the field itself is also very exciting. So maybe just for people out there who have not heard of Theragnostics, what is Theragnostics, and why are you so excited about it?
Yeah, so there had been a fair amount of debate that was settled a little while ago about whether the G in Theranostics should be silent or not. And the consensus finally ended up making it silent. So
I'm so embarrassed. I'm so
no. You pronounce it the way a lot of people do. Some of the Europeans still do also. So there's both ways of doing it. So you're pronouncing it the logical way. In other words, it's a combination of essentially diagnostics and therapeutics, and so it's therapeutics, diagnostics, or theranostics. But the G is pronounced by some people, but the trend now is to not. So it's Theranostics. And essentially, if you think of interventional nuclear medicine, where we have for decades been doing I-131 therapy that has now become a standard for treating patients with Graves' disease and also autoimmune thyroiditis, especially with an autonomous nodule like Plummer's disease, and also thyroid cancer. It's become a standard, and it's the element iodine. And it turns out that the thyroid really super preferentially takes up iodine in comparison to salivary glands and other areas of the body. It also turns out that Xofigo, or radium as an element, also can be utilized therapeutically in nuclear medicine to be able to preferentially go to bone and treat or at least palliate patients with diffuse metastatic bone cancer, particularly from prostate cancer. And so those have been around for a long time. Nuclear medicine physicians have mainly done iodine therapy. The radium therapy has been done by nuclear medicine physicians and radiation oncologists. And as time went on, there started to be a hunt for specific molecules that would look at essentially the surface of particular cancer cells. And so in the last few years, there has been an incredible race and gold rush involving tens of billions of dollars to develop molecules that not just like the elements iodine and radium, but that would be specific to being able to essentially attach themselves to particular types of cancer cells. And so for prostate cancer and neuroendocrine cancer, there were molecules that were developed that initially were used for imaging. So if I can essentially put a radioactive particle, gamma particle, or positron particle, and associate it with those molecules that are really expensive to develop and very customized and tailored for a particular type of cancer cell, it turns out that I can create an image of where those cancer cells are. So if poor grandpa has cancer outside of his prostate, I can image the cancer in the prostate, but now I can do something I can't do with CT or MR effectively, and that is look for evidence of the cancer in lymph nodes that may not be enlarged, but still have cancer. I may be able to find it in bone marrow and the lungs and in other areas. And so there was a whole generation then of people looking at this for diagnostic purposes. But then it turned out that you could use the same molecules, like PSMA, for example, or dotatate, to specifically label specific types of cancers for imaging, but also to be able to then attach a beta particle or an alpha particle to be able to kill the cancer cell. So a beta particle will disrupt the DNA cells, an alpha particle will essentially destroy the DNA. It's about 60 times as massive an alpha particle in comparison to a beta particle. And so it turns out that within the last couple of years, lutetium has been approved for being able to treat patients with neuroendocrine cancer and also treat patients with prostate cancer. And so those are both FDA cleared and also CMS and payer reimbursed. And so now we have about 10,000 molecules that are being developed around the world at academic and non-academic centers, where there is a race to find these for treatment for a wide variety of different cancers. And the advantage of this is really interesting. One is that you can target individual cells rather than radiation therapy, for example. The other thing is, unlike traditional oncology, we can actually see where our treatments go. So after I treat a patient with Lutathera for neuroendocrine cancer or Pluvicto for prostate cancer, I can see how much of my radioactivity that I administered went to the tumor, how much of it went to normal bone marrow, how much of it went to the liver, how much of it went to the kidneys. And now I've got the capability of being able to figure out what is the real actual quantitative dose that the patient got to a variety of different body organs and how much of it ended up going to the patient's tumor. And so we have the capability now, without most of the adverse effects of chemotherapy, using a mechanism different from immunotherapy, for example, to be able to come up with a new specifically targeted therapy. And the idea that people had about injecting nanobots or miniature submarines that would find a cancer cell and zap that particular cancer cell. I mean, this is the closest thing that we have to nanotherapy. And so it's a super exciting area of interventional molecular biology, essentially. And so as it turns out, it has become a subspecialty of medical oncology. The medical oncologists aren't able to do this because you need to have a radioactive materials license for radiopharmaceuticals. With additional training, the radiation oncologists are able to do this. And nuclear medicine and radiologists are able to do, physicians and radiologists are able to do this also. The radiation oncologists would argue, hey, you radiologists and nuclear medicine physicians don't really routinely put on a white lab coat and see patients. You're not used to all the other, modalities for treating cancer. This should be really radiation oncology because we, generically are the ones that kill cancer with radiation. The nuclear medicine and radiologists would argue, I would suggest more persuasively, but of course I'm biased, but would argue very persuasively that this really involves a combination of imaging with PET, CT, and SPECT, where we image the patients, we make determinations based on the images, we then do dosimetry after the therapies, and we then tailor the subsequent therapies based on the dose delivered to the tumor and the dose delivered to marrow and to liver and kidneys and other organs. And that we essentially are able to do the advanced dosimetry and be able to do those calculations and be able to use imaging. And so the idea of theranostics, which is therapy plus diagnostics, requires somebody that's able to do the diagnostics part at a really high level. And so the idea of creating a subspecialty in nuclear medicine and radiology of not interventional radiology or diagnostic radiology or nuclear medicine, but essentially interventional molecular imaging and therapy is this new emerging therapy, is this new emerging specialty that tens of billions of dollars are being invested into for new radiopharmaceuticals for almost any cancer that you can imagine. And it's been really effective for prostate cancer. It's first line or second line therapy for neuroendocrine tumors. And there's a whole host of new tumors that essentially will be treated with radiopharmaceuticals. The problem that we have right now is that there's a huge mismatch between the number of new radiopharmaceuticals coming out, the need for clinical trials, the number of patients who should be getting this therapy, and the tiny, tiny number of inpatient and outpatient centers that are available to give the therapy. And so most of cancer care is delivered on an outpatient basis. And that cancer care delivered on an outpatient basis, in general, is begging at this point for outpatient radiopharmaceutical therapy. The challenge that you have if you're an outpatient oncologist is that most of these women and men who are medical oncologists are reluctant to refer to academic centers because many times their patients then are taken over for all of their oncology care at the academic centers. And so the idea of having an outpatient subspecialty where you can refer your patients for maybe the 36 weeks of 6 treatments for their prostate cancer, and that the patient's therapy is customized and personalized based on the dosimetry, and the patients are then given back to the medical oncologist, there's a huge need for that. And so in my interest in doing what I tried to do disruptively for filmless radiology and digital radiology, I'm really interested at this point in my career in being a pioneer in disrupting the delivery of oncology care and in being a disruptive, in a positive way, of course, influence on nuclear medicine to offer this brand new specialty to nuclear medicine physicians and radiologists, but with this very rigorous dosimetry that's done on the patients, where we do 3 measurements after each one of their treatments to create an integral curve so we can figure out what the cumulative dose is after the therapies and then tailor our subsequent therapies based on that. Right now, there is not another practice in the US that we're aware of that is doing that rigorous of a customization or personalization, certainly not on a national level. So the idea is to combine my interest in informatics and computer systems and create an a priori data-driven business with a couple of former residents at the University of Maryland and create United Theranostics, which we want to design to be a national practice where we have essentially easy access to all patients throughout the US to being able to get clinical treatment for their cancers that are treated by this radiopharmaceutical therapy, and also to offer a means for the dozens of clinical trials that need to take place to investigate these radiopharmaceuticals. Whereas at this point, there are very few geographic locations in the US to gather a diverse population for being able to develop and test these new radiopharmaceuticals in a clinical trials environment. And so, what we're building will be the largest national outpatient nuclear medicine subspecialty practice, the largest clinical trial network for radiopharmaceuticals, and the largest clinical care network for theranostics or radiopharmaceuticals in the US. And so at this point, I'm in the process now of making the pivot from being the researcher, the person that worked inside of the National Cancer Institute, University of Maryland, Department of Veterans Affairs, being the researcher, to actually being somebody who does the brick and mortar execution of building up clinical sites and having a really high standard of care for treating patients and trying to create something that gives access to this brand new emerging field. And so the idea of being a disruptive pioneer, first in digital radiology, then in artificial intelligence applications in radiology, and then in advanced visualization in radiology, and now in this new emerging field of oncology, has just been a natural progression of where I want to see, my career go. And so at this point, rather than kind of slowing down at the University of Maryland and VA and some of the other things that I've been working on, I'm in the process of pivoting to essentially devote the majority of my time to trying to set up this national enterprise. And we have huge support from the Society of Nuclear Medicine. I'd like to look at revamping radiology and nuclear medicine training programs so that there can be training in this interventional molecular imaging and therapeutics, where we have more of an emphasis on biomolecular medicine, which I think, would be really interesting to introduce in radiology and nuclear medicine, and to creating this new emerging field. And I think it's going to have a major impact on cancer care in the future. So the same way that it was just too fun to pass up the idea of being the first pioneer in the world to create the first digital department, and having really fun and being really energized by that concept, in a very similar analogous way, I'm really energized by the ability to essentially become a pioneer from the radiology and nuclear medicine perspective on a high level of practice that is data-driven and is based on quantitative, continuous feedback of data, and using those data to be able to put back into treating our patients. And so for me, I've been having a lot of fun, as I was mentioning to Mitch when we talked the other day, kind of with this brand new specialty, and hoping over the next few years it'll be something that I can learn more about, and that I can sort of make available to patients, and also serve as mentor to trainees that might be interested in this exciting new field. What I'd love to do would be to be able to attract the best and brightest medical students into the specialty of nuclear medicine and radiology, who might be interested in molecular biology and in the implications of being able to do these molecular interventions. And so that's kind of the story of why I'm really interested and excited about what we've set up with United Theranostics.
There's so many different directions we could go in this, but I want to be mindful of everyone's time. I have one last question about this topic, and then we'll close with a few rapid fire. Okay?
Yes, love it.
The question is, in terms of the actual treatments that are being used molecular treatments for neuroendocrine therapy for prostate cancer.
Yes.
Where do we stand in terms of effectiveness for these particular treatments in terms of actually, increased quality of life and length of life?
Yeah. So right now there are 2 FDA cleared, CMS approved, and insurance approved applications. There will be many more coming on board. For neuroendocrine tumors, the treatment with Lutathera or Theranostics treatment is first or second line treatment, and it has a major positive impact and could potentially, be curative, but certainly has, significantly increased patient life expectancy. For prostate cancer, right now it's officially approved as last line therapy, and so one of the challenges is that these patients, by the time they get to us, their other option really is hospice care. And so they tend to have renal dysfunction. They tend to have, be really relatively medically debilitated. And so, in general, people have been seeing increases in patient life or quality of life along the lines of 3, 4, or 5 months, something in that neighborhood. What is being tested now, and everyone is confident that it will be FDA cleared and CMS approved for using this as a much earlier treatment for prostate cancer, maybe second line therapy. And the idea of being able to use it in combination with other types of therapy is something that's being explored. I believe that it will have a much more significant impact on prostate cancer patients if it's used earlier on in the treatment and along. It may be something that would be used prior to surgery, for example, rather than waiting for patients who are castration-resistant diffuse metastatic disease, which is where it's used now. The reason it's being used there is because the trial that was done was using that population, and that's what they got FDA cleared on. People are essentially going off-label and using radiopharmaceuticals as the oncologists are asking us to use it earlier on or in combination. But we're waiting for it to be essentially officially cleared specifically for earlier instances. And then in the next few years, even if 1% of those 10,000 molecules actually end up going through the process to clinical trials, we're talking about 100 new molecules, 100 new radiopharmaceuticals for a wide variety of different cancers.
All right.
Okay.
First rapid fire is, what is one medical truth that very few of your colleagues agree with you on?
Yeah, so I think one medical truth that very few of my colleagues would agree with me on would be that Theranostics is going to become a predominant, really impactful and important therapy in cancer care moving forward. I think that right now it's playing a relatively smaller adjunctive role. And I believe, and I think most of my colleagues would be skeptical at this point, that it's going to be playing a much more major role over the next few years.
Like more important than radiation oncology, or about that, like what that is now, or like where would you put it in terms of?
Yeah, in other words, I think radiation oncology is going to be utilized when the cancer is localized, for example, specifically to the prostate or specifically to a squamous cell carcinoma in the neck or a specific area. But so often with metastatic disease, then it really becomes, something that is not really appropriate for radiation therapy. And so I believe that it's going to become a strong adjunct to radiation therapy. I think there'll be radiation therapy, immunotherapy, CAR T therapy. I think chemotherapy will become, much less often utilized as kind of a general mechanism for treating patients. And I think we're going to have a wide variety of very specific targeted molecular therapies that will become a predominant mechanism for treating patients in cancer. And I think at this point, most people would say that's overly optimistic for theranostics and radiopharmaceuticals.
Next question. If you had unlimited money for a single randomized controlled trial, what would you spend the money on?
Yeah, so I think what I would do would be to spend the money on breast cancer. and looking at the ability to be able to develop molecules that are specific to a variety of different breast cancers, and developing a portfolio of molecules that would be specific to a wide variety of different types of breast cancers. And I would like to try and utilize this for that type of therapy in patients that have developed regional or a metastatic breast cancer. So I think that would be the one area that I would do. There's so many ways I'd love to do clinical trials, and any one is arbitrary, but if you rapid fire force me to pick one, that's what it would be.
Last rapid fire. What is one important scientific article that you believe more physicians should be aware of?
Yeah, so that's a tough question. And so I think that probably the one that comes to mind is actually one that we've written recently and published that will be a relatively minor paper as far as the way it's received, but has major implications. And that is the ability to be able to do 1/60th dose PET scans that would allow one to be able to use molecular imaging at the same radiation dose as a chest radiograph, a chest PA and lateral. And so the potential to be able to do specific molecular screening at doses that are comparable to chest radiographs, and making nuclear medicine screening studies a possibility, whether or not it's FDG, imaging or PSMA or whatever it is. I think being able to do molecular screening in large amounts with ultra low doses really has major implications. And so if I had to pick the one that pops into my head, I would have to, in a self-aggrandizing way, suggest that that's the first one that popped in my head. I think if you gave me some more time to think, it would be unlikely I'd pick my own article, but that's the first one that pops into my head.
Well, excellent. Thank you so much for joining, Eliot. It's been a real pleasure for us.
Pleasure is mine. Thanks for the great questions and the opportunity to swim down memory lane. I don't get a chance to do that all that often. One of the topics that I give a lot of talks on is the future and where things are going in the future with AI and with medicine in general. And so being able to go in the opposite direction and go down memory lane of some of the history, and even some of the history of Theranostics and PACS, was a really fun exercise. So thanks for walking me through that. I really appreciate the opportunity.
Before we close, if anybody is interested in learning more about you or your work, where should they go on the internet?
Yeah, so from a commercial plug perspective, United Theranostics would be unitedtheranostics.com would be a great place to go. But I have a huge amount of YouTubes and lectures and things. If you just Google my name, Eliot, Eliot, Siegel, Siegel, then lots of the talks I've given are online. Lots of materials I've talked about are online also. And so that might be one source to go to. And I think so many people are not aware of Theranostics, even in medical oncology. And so I think learning more about that, I would love to see. And I'd love to see more students who are at the undergrad level or in medical school, or even folks who are doing residencies, really seriously consider Theranostics or interventional, molecular imaging and therapy as a career, from a lifestyle perspective, from a financial perspective, but more importantly, from an impact perspective. And I think there's got to be a subset of folks who are doing diagnostic imaging who want to interface directly with patients and be able to essentially be, in some ways, kind of oncology primary care providers, but with a super subspecialty. And so, if there are folks out there that have that combination that I think is somewhat unique, of wanting to interface with patients, but yet love all the cool things related to diagnostic radiology and nuclear medicine, I would love to see them learn more about Theranostics in general. So really appreciate you guys allowing me to be able to discuss this for your large audience.
Well, thank you for joining us. It was our pleasure.
This podcast is for educational and entertainment purposes only. We do not endorse any healthcare providers or treatments. Our views do not represent the views of any official organization or institution.
If you'd like to support us, subscribe to this podcast wherever you get your podcasts. Leave us a review, preferably a phenomenal review. Visit us at externalmedicinepodcast.com and tell your friends.